Hi everyone. Today we are moving into our quantitative research portion of research methods. I totally understand this is going to involve some math. Some of you are not excited about it. I'm going to try to make this as easy and as straightforward as possible. The thing is that you need to understand this, even if you don't go on to do quantitative research. You need to understand the math regarding quantitative research because the numbers are what helps us to predict uh, future phenomenon. So part of the reason that we do quantitative data analysis is for two reasons. Number one, it describes the current set of data, and number two, it helps us to predict within a probable range of possibilities how likely it is that new data is going to sort of fall within these small parameters that we've created um, based on old data. All right. So we're going to get through all of this. Do the best you can. I'm going to ask you to pause the video at certain points to try to work out some of the math on your own. The math is important. You're going to need to do the math for your exams. You're also going to be able to need to do a little bit of math for your final research project, your quantitative research project. And I'm just going to show you how that works. All right. So as we go along here, try to do the best you can to follow along. We're going to have some in-person classes as well so that I can answer some questions for you. Okay, so type of data analysis. The first is what we call descriptive statistical data analysis. So it's a quick way to summarize the current data that we have access to. So what we do is we gather a lot of data. Now you can do this with regard to a Likert scale, for instance, right? On a scale of 1 to 5, how much do you enjoy Dr. Phillips's class? And right now you might say a 2, right? I don't really enjoy it that much because we're dealing with normal distribution bell curves. But it's a quick way to sort of understand where the data ended up based on an average. So for instance, you all take an exam in this class. What we can do is we can take all of your scores, your test scores, we can put them into a chart, we can put them onto a bell curve, and then we as a class can sort of see on average where does the class fall with regard to their test scores. All right, so it just describes the current type of data. You might do this with regard to people's heights. So for instance, the National Basketball Association is going to have a draft of new players. You might be very interested in figuring out how tall on average those players are. You take all the individuals who were drafted by NBA teams this year, you take their heights, you put them into your statistical model, and then you're gonna calculate some numbers, and you're gonna figure out, okay, the average height of the current incoming NBA player is, I don't know, 6'7". All right. You might be really interested, if we continue to go with sports for a while, right? You might be really interested what the likelihood is of rookies with regard to the points that those rookies score in the National Basketball Association, right, in the NBA every year. So what you're going to do is you're going to follow everybody who's coming into the NBA this year, who's a new person. You're going to calculate how many points they put up every game, and then you're going to say, okay, the average rookie this year scored 7 points per game. All right, that's the descriptive analysis. All right, you have a population and you want to figure out what the average numbers are for people within that population. All right, now the inferential statistical data analysis, this comes to what we call the predictive quality part. All right, so descriptive just describes the data you have. Inferential, what it does is it takes the data that you have and it tries to generalize it to the larger population in order to figure out how that data can help predict future behavior. So for instance, all right, you have figured out that the average height of incoming basketball players this year is 6'7". Based on that number, I can predict for next year's draft what the average height might be. I have now figured out what the current NBA rookie is scoring with regard to points. I can start to predict how many points future NBA rookies are going to score once they're drafted in the NBA. All right. Now, if we get a little bit more fun and a little bit more creative with this, This type of analysis goes into things like sports betting. All right. So based on somebody's past performance, people who set the odds with regard to gambling say, we are predicting what their future performance might be with regard to who's going to win the Super Bowl. How many points is LeBron James going to score? All right. This is all within the realm of analyzing data from the past in order to try to predict what is going to happen in the future. All right. Those are the two reasons that you analyze data. I want to understand the current moment, and then I can take that current information and I can predict with some sense of accuracy, some sense of probability, what will happen in the future with regard to similar situations. So let's talk about how this works. All right. If I'm doing some sort of quantitative research, I might give out 100 surveys. So I go and I find 100 people. I give 100 surveys, and each survey has 20 questions. When I get those back, I now have 2,000 numbers, and you say, okay, what do I do with all those numbers? All right. So I hand you a survey. That survey has 20 questions on it. You think about the evaluations you fill out for your professors at the end of the semester. If I have a class of, if I have 100 students, I give all of them student-teacher evaluations. Each of them fill it out. They're 20 questions long. I get all these numbers back, and I'm like, what am I supposed to do with all these numbers to figure out, was my class useful, was my class not useful? What I have to do then is I have to take all these numbers and I put them into a statistical model. So there's three things that you probably learned from math class before that are the first three things we're going to be interested in. The first is the mode. So what is the score that occurs most frequently? All right, that's the mode, the score that occurs most frequently. So let's go back to this idea of height in the NBA. All right, the average incoming basketball player to the NBA might be a height of 6'7". All right, that could be the most frequent height of all the players that we have. Most players are 6'7". All right, just from a numerical situation. All right, the median is the number that is right in the middle. All right, so what that means is you're going to have 10 players line up by height, 4, 5, all the way to 10 players by height, right? And you're going to figure out, okay, the player with the absolute middle height is, let's say they're 6'9". So let's say you have some people way up here who are 7 feet tall. You have some people down here who are 6'5", right? But the player right in the middle, if I count from the outsides inward, the median is the exact middle person. All right. Now, in a survey of just 10 people, your number 5 and number 6, they're going to share the middle. So what you do is you're going to average those two. All right. So that's what the median is. It's the exact middle number. If I just take all the numbers, I line them up in numerical order. I start on the ends. I work my way toward the middle. Whatever number's in the middle, that's the median. All right. The mean is the average. Now, this is what is super important to us. The mean. All right. These other ones are good to know. Mode and median are good to know. The mean is what's important to us. The mean is the average. Right? So if I have a bunch of players of different heights, I want to find out what the average height is. Hopefully you all know how to do this from Math 101. Is I take all of the players' heights, I add them all up, and I divide by the amount of players that I have. So if I have 10 players, I add up all their heights, I divide by 10, and I might come off with a mean of 6'8" and 1/2 inch. All right. So that's what the mean is. It is the average, which is different than the median. All right. So know what the three of these are. There's plenty of resources online to get a little bit more information. But again, the mode, the number that occurs the most frequently. So you might have 3 players that are all 6'6". 6'6" occurs a lot. So I just noticed that as the mode. The median is the exact middle number when I start on the outsides and I work my way toward the middle, whatever the middle number is. The mean is the average. So you add everything up, you divide by the amount of data points you have, and that's the mean. All right, so for this set of numbers, all right, the first thing you have to do for any set of numbers that you get, the first thing I recommend is you put everything in order. All right, because if you don't put anything in order, it's really, really difficult. So in order to find the mode, the mean, the median and the mean, we're going to first put these things in order. So I have a 1 here, 1, 2, 3. I have 4 number ones. Then I have 1, 2 twos. I have a 3. I have 2 4s. Let's see, I got a 5. I have a 6. I have an 8. I have 2 9s. And I have an 18. All right. All right. Okay. So let's start off with what is the mode? What is the most frequent number that we see? And we look at this set and we have 4 number ones. So the number 1 just appears the most often. So number 1 is our mode. The median is the exact middle number. So we start on the outside, right, and we work our way toward the middle. So I can get a different color here. I lop off the 1, I lop off the 18. Lop off the 1, I lop off a 9, a 1, a 9, a 1, an 8. I get rid of a 2, I get rid of a 6, I get rid of a 2, I get rid of a 5. I get rid of a 3, I get rid of a 4, and right in the middle is a 4. So the median is 4, because that's the middle number as I start from the outside and I work in. And then finally, what is the mean? So you add everything up, you divide by the amount of data points there are, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 15 points of data. All right, so we're going to add all these numbers up. Bear with me for a second. 4 plus 1 plus 9 plus 2 plus 6 plus 3 plus 1 plus 1 plus 8 plus 5 plus 2 plus 1 plus 4 plus 9 plus 18. I have 74 divided by 15. 4.9 is my median, mean. All right, the average of all those numbers is 4.9. All right, so you're welcome to do the math, to double check my math. We'll talk about it in class on Friday. Okay. Now there are these things called outliers as well as ranges. This is not something that we're going to dive deeply into. You should just know that they exist. Outliers are numbers that are sort of so far outside what seems to be normal, and sometimes researchers just get rid of them. So a number like 18 just seems so high, it's like, let's just get rid of that. All right, it's an outlier. The range is the distance between the highest and the lowest score, so it's simple subtraction. So 18 minus 1 is 17. So there's 17 is the range between the high score and the low score. So our data traverses 17 spots. All right. Now, this is where we get into normal distribution bell curves. You all have probably seen a bell curve before. What a bell curve is it looks like this. All right. And what it's trying to do is it's trying to predict with some sort of accuracy how many pieces of data are going to fall close to the average, close to the mean. All right. So this high point says the vast majority of data is going to somehow be around this mean. All right. Now there's going to be some data that's way up here. It's like super special data. It's in the 0.5% of sort of top end data. There's going to be data way down here that's in the 0.5% of sort of low end data, right? There's going to be some people who are above average, right? There's going to be some people who are below average, but the majority of people, the majority of data points are going to be somewhere here in the middle, hanging out around the mean. All right, and that's what we're trying to figure out. All right, so we're going to do a couple of these on our own. or with each other, and then I'm going to ask you to pause the video, and then you can sort of do some math on your own, and then when we get to class on Friday, I'll give you some more data to look at with regard to the mean, okay? So the first thing you want to do with any set of data is you want to find the mean. What is the average score of this data that I have in front of me? All right. Then you're going to find what's called the deviation scores. All right. And the deviation scores are how much difference is there between each individual set of data point and the mean. All right. I'm going to go through more of this in a second. All right. And what this will help us to do is it's going to help us to figure out with some semblance of accuracy how much we can predict the data that we have will be close to the mean. So for instance, all right, we have various sets of numbers. All right, we're going to call this set of number, we're going to say that this is height. All right, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So let's say there's 13 students in the class, and this is the height of people. So in inches, right? So 70 inches, 72 inches, 65 inches, etc. This is how tall people are in the class. All right. So what we could do is figure out with some sort of accuracy is if you are the person who is 77 inches tall, how close are you to sort of being in this like top 1% of people with height? If you're the person who's 60 inches tall, you're probably down here in the low estimate with regard to average height. All right, and then there's going to be a lot of people who kind of congregate in here right around the mean. All right, okay. So how do we figure out what the bell curve looks like? All right, the first thing we want to do is we're going to actually use this set of numbers 10, 7, 5, 2, and 1. All right. Because what we're going to do is we're going to find what's called the standard deviation. And a standard deviation, what that means is with each set of data, how close is that piece of data to this middle number, to this mean? All right. And the closer you are to the mean, the closer you are with regard to your total standard deviation from the mean. All right. Most things, when you plot them on a bell curve, are within one standard deviation of the mean. Most things are pretty close to average. All right. So, and then again, what we can do with this information is, let's say that we take height. The reason that we would find the standard deviation of the class is because let's say there's 13 people in the class, and then tomorrow we're going to add a 14th student. So before that student even comes into class, what we can start to think about is, with some probability, we can predict how tall that student is who's going to enter into our classroom, even though we've never met that student before. All right. You can say, well, how useful is that? Well, with regard to that, it's not that useful. But you start to think about all of the other types of numbers that we need to predict in our life. And then we start to say, oh, it could be pretty useful knowing the probability of these things happening. So again, sports gambling. All right. We want to know with some sort of probability how likely it is that LeBron James is going to put up 20 points, in tomorrow night's game, right? Well, if we know about how many points he scores all the time, we can predict with some sort of probability what is the likelihood that he is going to score 20 points tomorrow, all right? As opposed to scoring 0 points, as opposed to scoring 80 points. Now, is it possible that LeBron James, plays in his next game and he scores 0 points? Yeah, but that probability is very low. Is it possible that LeBron James plays in his next game and he scores 80 points? Yeah, but that probability is also very low because it's on this sort of high end of the standard, this standard deviated bell curve. All right, it's normal distribution bell curve. All right, so let's look at this first set of data: 10, 7, 5, 2, and 1. All right, this is on page 299 of your textbooks. So the first thing you always want to do is you want to find the mean. All right, so we have we have 5 numbers here. They represent whatever it is you want to represent. It could be some sort of Likert scale. On a scale of 1 to 10, how much do you whatever, right? So the first thing we want to do is we want to find the mean, right, which is finding the average. So we add all these numbers up and we divide by 5, and that gives us a mean of 5. So 10 plus 7 is 17, plus 5 is 22, plus 2 is 24, plus 1 is 25. 25 divided by 5 sets of numbers, we have an average of 5. Our mean is 5. Now what we want to try to do is figure out the standard deviation for this set of numbers. When I plot this set of numbers on a bell curve, all right, my mean is a 5. How close are all of these numbers to 5 with regard to standard deviations? All right. So in order to do that, we do this function which is known as the sum of the squares. All right. So what we have to do is we first and foremost have to figure out what is the deviation for every individual score from the mean. So you know the mean. After you know the mean, this is what I recommend you do. You write down all of the numbers in a nice little column like so. Now you want to find the deviation of each one of these numbers from the mean. And the way you do that is through subtraction. So 10 minus 5 is 5. 7 minus 5 is 2. 5 minus 5 is 0. 2 minus 5 is negative 3. 1 minus 5 is negative 4. All right. So now we have the deviation of every individual score from the mean. 10 deviates from the mean of 5 by 5 places. 7 deviates from the mean of 5 by 2 places. 5 deviates from the mean by 0 places. 2 deviates from the mean by negative 3 places. 1 deviates from the mean by negative 4 places. All right. Now what we have to do, all right, is we have to take all of these numbers, all these deviations, and we have to square all of them, right? So this is what's called the sum of the square function. And the reason you have to square all these numbers is because you have to get rid of these negative numbers. Because if you don't give the negative numbers and you just do the sum of all these, it's always going to end up being 0, right? So if you add 5 plus 2 plus negative 3 plus negative 4, it's going to end up 0. It's going to end up 0 on every set of data that you have. So you always need to square these numbers so that you can get rid of the negative numbers in order to complete the function. All right. So you add together all of these scores. All right. You square you square all of these scores and then you add them together. All right. So 5 squared is 25. 2 squared is 4. 0 squared is 0. Negative 3 squared is 9. Negative 4 squared is 16. You add it up. You have 54. 54 divided by 5 sets of numbers is 10.8. 10.8 is the variance. Now what you have to do, because you squared the numbers, you have to find the square root of this number. 10.8, the square root of 10.8 is 3.29. 3.29 is one standard deviation. All right. Now, remember this number, 3.29. What 3.29 means is that every number that we now predict with regard to the set of numbers we have is going to be within 1, 2, 3 standard deviations. We can predict with some sort of accuracy that new numbers that come into our data set are going to be within 1 standard deviation with regard to a 68% probability rate. All right. So this is what standard deviation is. When I make a bell curve, the reason I make a bell curve is because I want to predict with some sort of accuracy what future numbers are going to look like. The way a standard normal bell curve looks, the way that it looks is that within 1 standard deviation, I can predict with 68% accuracy that all of the new numbers that come into my data set, I can predict with 68% accuracy that 68% of all the new numbers that come into my data set are going to fall within 1 standard deviation. I can predict with 95% accuracy that all new numbers that come into my data set are going to be within 2 standard deviations. And I can predict with 99.7% accuracy that all new data that come into my data set are going to fall within 3 standard deviations. All right. Okay, so let's go back to our old data set where we get this standard deviation of 3.29. What this means is that my mean is 5. If I add 3.29 onto that, I have 8.29. And if I subtract 3.29 from 5 minus 3.29, 1.71, right? So what this standard deviation allows me to do is predict that the new numbers that come into my data set, 68% of those new numbers are going to be within a range of 1.71 and 8.29. All right. Now, again, this can be helpful with regard to sports betting. So if I know that on average, let's say LeBron James dunks a basketball 5 times per game, and I want to make a bet with my friend, all right, I can predict with 68% accuracy that in the next NBA game that LeBron James plays, he is going to dunk a basketball either 1.71% of the time, or excuse me, 1.71 times to 8.29 times. All right. I can predict with some accuracy that the range of dunks that LeBron James is going to have in that next game is somewhere between 1.71 and 8.29. I can predict that with 68% accuracy. Now, is it possible that LeBron James dunks the basketball 10 times in a game? Right? Yes, that's within 2 standard deviations. Is it possible that he never dunks the basketball in the next game? Yes, that'd be down here with like within 2 standard deviations in the other direction. All right. So what standard deviation does is it helps me to predict with some sort of accuracy within 68%, 95, 99.7%. That's the way a standard deviation works on a normal distribution bell curve. All right. Within 1 standard deviation, I can predict with 68% accuracy. Within 2 standard deviations, I predict with 95% accuracy. Within 3 standard deviations, I predict with 99.7% accuracy. All right. Let's go on to one more example. Let's not worry about these visuals and charts for the moment. Let's go on to this one more example. All right, we're just going to do one more example together, and then again, we're going to come together on Friday to answer questions. I know that this gets clunky, especially when you're trying to teach it via, PowerPoint and Zoom as opposed to being in the classroom. All right. So what we're going to do is we're going to do the example with regard to finding the heights of our fellow classmates in class. All right, so we have a data set of 13 students here. All right. And I want to describe and I want to predict what this data set can do. So the description part is, what does the data set actually tell me about the average height of the student currently in my class? The prediction is, when new students come into my class, I can predict how tall they might be. All right. So what you want to do with this data set, right, is I want you to find the mean for these numbers, and then I want you to make a normal distribution bell curve. All right. With regard to 1, 2, and 3 standard deviations. So if you want to pause the video right now, cool. I'm going to show you in the next 5 minutes what this looks like when it comes to taking these numbers, taking the data set that you have, and charting it on a normal distribution bell curve. All right. So if you want to pause and try to figure out these numbers on your own, please do. The first thing you want to do is put these numbers in order. Right now they're all out of order. Then you want to add all these numbers up. You want to divide by 13 because there's 13 sets of data, and that gives you the mean. And the mean is always that middle number at the peak of the bell curve. Okay, so this is what these numbers will look like when you put them in order. So I took these numbers here, and this is just put in order. These red numbers are just put in order. So we can get rid of these because I have put them in order. When I add up all of these numbers together and I divide by 13, I get an average height of 68. So the average student in my class is 68 inches, which is 5 foot 8 inches tall. All right, that's the average height. So now I've just described the set of data. I've asked you all to tell me how tall you are. I've looked at the numbers and I'm like, I'm really interested to see how close to average you are and what the average height is. And I figured out that the average height of student in my class is 68 inches. All right. The predictive quality is how tall will future students in my class be. I can start to predict that based on current information. Now, height of students probably isn't very important, right? Test scores, you can do this with test scores, like what's the average on the last test that we all took together. You could look at this as graduation rates. So I could track you all for the next 4 or 5 years and see how many graduate, how many transfer schools, how many take a year off, how many decide not to graduate, not to continue with school, whatever it is, right? So these numbers are useful with regard to me setting up future classes because I'm trying to predict how to make my class more accessible to students. So if I want to take the class average of a 72% and I want to figure out a way to bump my class average up to an 82%, I use previous information to teach the class differently each semester to help boost those test scores. All right. So I found the mean, and the mean is 68. Now what I want to figure out is how much from each set of data does the mean deviate. So I take every piece of data and I subtract 68 from it, which is the mean. All right, and I've already done this, my sheet of paper in front of me. So 60 minus 68 is -8. 62 minus 68 is -6. All right, 65 minus 68 is -3. And we go on like that. All right. So let's go ahead and erase this. All right. So we have 60 minus 68 is -8. 62 minus 68 is -6. 65 minus 68 is -3. And we do that for every other piece of data. All right. So after you have all these differential scores, right? What you need to do is you need to square every score that you have. So -8 squared is 64. -6 squared is 36. -3 squared is 9, right? And I go on and on and on with all 13 pieces of information, all right? When I add up all of the numbers that have now been squared, I get a very large number. Hold on. I only wrote down the final. 230. When I add up all of the squares of these numbers minus the mean, I get 230, right? Then I need to take 230. I need to divide that by 13 because there's 13 pieces of data. I get 17.69, right? 17.69 is my variance. Since I squared all the numbers, I now have to find the square root of 17.69, and that equals 4.2. Okay, so what do we do with 4.2? 4.2 is our standard deviation for this set of data. All right, so 4.2 inches is what it ends up being, is what the number that we use to chart this new bell curve. All right, so here's my bell curve. This is my mean. My mean is 68 inches. The average student in my class is 68 inches tall. All right, 68 inches plus 4.2 inches is 72.2 inches. 68 minus 4.2 inches is 63.8 inches. All right. So now what I can predict is that 68% of my students are going to fall within 1 standard deviation of the mean. So 68% of my students are going to be between 5'3" (.8 inches) tall and 6'0" (.2 inches) tall. So 63.8 inches tall, 72.2 inches tall. 68% of my students are going to be between these two heights. All right, that's 1 standard deviation. If I go out to 2 standard deviations, I take 72.2, I add 4.2 onto it again, and now I have 76.4 and 59. 63.8 minus 4.2 is 59.6. And now I've gone out to 2 standard deviations. So now I can predict with 95% accuracy that 95% of my students are going to fall between 59.6 inches tall and 76.4 inches tall. All right. Then you can take that up to 3 standard deviations for 99.7% accuracy with regard to prediction. All right. So that's how this standard deviation exercise works. What I'm hoping that you will do between now and Friday is that you will kind of follow along and do this math kind of with me as I'm doing it. You rewind 10 minutes and kind of go through that, and just make sure you know how the operations work. Then when we get together in class, I'll answer some questions. We'll do some more examples. We'll explain this a little bit more deeply, right? But again, just know the function right now, and then as we get into class, we'll sort of talk through more about how this is useful and what you can use these bell curves for, all right? Again, this is a normal distribution bell curve, right? There are lots of forms of bell curves that are skewed and all this. Let's not worry about any of that. We're just talking about normal distribution bell curves, all right? So again, a bell curve describes data. So I take this set of data, I figure out what is the average height of my students, and then then you can figure out, okay, am I average? Am I below average? Within how many standard deviations am I of the average? If you're a person who's down here, who's the person who's only 60 inches tall, you're sitting down here like I'm I'm 2 standard deviations below average. If you're up here and you're 77 inches tall, you're able to say I'm 2 standard deviations above average. All right. If you're a person who's 68 inches tall, you say I'm right at the average. All right, so that's describing the current data. And then there's inferring for future, right? We're trying to predict the future with these numbers. And again, if new students come into my classroom, before I even see those students, I can guess with some sort of accuracy, with 68% accuracy, that the new student is going to be between 63.8 inches tall and 72.2 inches tall. I can predict with 95% accuracy that new student is going to be within 59.6 inches tall and 76.4 inches tall. All right. So that is what standard deviations are. Know the function, know how to sort of just know how to chart this stuff on a bell curve right now. We'll get into some Q&A on Friday and next week as we start talking about your next projects. But for right now, all I want you to do is grab a piece of paper, take this set of data that I've already found the answers for, and I just want you to sort of do this set of data, right? Let's get rid of that because that's out of order. Take this set of data in red and just sort of write it out longhand, the steps. So the first thing is find the mean, and then you take each piece of data and you subtract the mean from it. So the mean is 68, so 60 minus 8, 62 minus 8, 65 minus 8. Then you take those new sets of numbers and you square all of them, right? Then you take those squares, you add up all 13 of those new numbers, right? Then you divide by 13 to get the variance. Then you take the square root of that. All right. So go back through this video and just know how the function works. Just know how to get to 4.2, right, with regard to this set of data. And then we'll sort of we'll talk more through this on Friday when I see you in class. All right. That's all I have. I will talk to you all later.